All right. Well, welcome everyone to our workshop today on fairness in AI. We're going to be talking about some methods regarding how to make your models more fair and equitable in practice for society. And so we can have inclusive data science for all. So we'll talk about a little bit more, much more, about the meaning of what I just said. But first, let's have a little questioning. So let's see. So let me propose this hypothetical situation. See. So let's say that you just have this data set fall in your lap and you are instructed by your supervisor or whomever to predict whether a person will get COVID just based on some factors or features that are now in the data set. So let's just say that those could be some demographic features which you may or may not choose to include, maybe some information about health or income, job, activity level, those types of things. Let's say, for instance, also that the data is balanced somehow magically, and you have maybe 500 COVID or 500 non-COVID, or however many to make that equal in your samples. And so let's say you train your model, you have done quote unquote everything right. You don't have any data leakage. You have really, you have split your data well. You've done cross-validation. You've done hyperparameter tuning. You've done the whole shebang. And so now at the end, you get these blessed performance metrics, and you find that the accuracy of your model is about 96%, your sensitivity is 98, your specificity is 94, and then you have these relatively low false positive and false negative rates. So you go to your boss and you're trying to figure out, is this acceptable? Like, these are great numbers, but is this acceptable? And so your boss says, yeah, 95% balanced data set, your rates are looking really good. So things might feel good and you're feeling really great about this. So here's a question for you. Is this a good model? And so you can use your reactions in the reactions pane. There's a zoom button that looks like this at the bottom of your screen. And go ahead and give this green check if you think that, yes, this is a good model. Red X if you think, no, it's a bad model, or you think it's a trick question, even though you want to say yes, but the fact that I'm asking is very suspicious. All right, let's see. Oh, I can't see the counts of them, but it looks like a lot of people are suspicious. So I'm right there with you. So with me, I really, really want to say yes, because a lot of these metrics are just looking so good. And if I were to look no further than this, I might think, this is whoa, like I cannot believe that I trained such something fabulous with these great performance. Maybe everyone's gonna know whether they have COVID or not based on my model. Well, let's say that you believe that. And I mean, it looks fine from this perspective. And so you start getting feedback after you've deployed your model. So you're looking at your false positive rate and false negative rate. Things are looking really good. But you start hearing back from your users. And so it seems like maybe from all the colleges, like this model is just the best. Like all the chancellors are just screaming your company's name, and they're just really loving the way that this model performs because it's really helping them. On the other hand, maybe the general public, maybe general hospitals and nursing homes are saying that this model is just filth. It's garbage. It doesn't work at all. And so you're very confused because you remember that your model metrics they're looking really, really good. And you start thinking, well, maybe it's user error. Well, perhaps it's not that. So maybe you might think, well, let me just go ahead and take this look again. There's no telling it's code. Maybe I did make an error and I just want to make sure. And I will not have these people besmirching my good name with their words. So then you look again. And you decide, you know what, now that these people are specifically making this point, which seems to be separated by age, let me go and look at that specific factor. So maybe you decide indeed to do that. So now you go and look at your data, you do your EDA, you look at your variables, and you find that 90% of your data set is quote unquote young, whatever that is to mean. And then 10% are not young. That's interesting. And then whenever you go to look at the performance on the young people, somehow magically, and assuming again, everything we've done correctly, somehow this magically happens, that we have this really really great accuracy on the young people. But if we were to go and look at the not young people, the performance of the model on that subgroup, we would see that not only is there a really strong class imbalance, so maybe almost there's no representation of the COVID patients, and they're all non-COVID. So maybe you don't even have a way to learn about this other population. And you find that in this case, on this subgroup, you have 50% sensitivity, 70% specificity, and you have very high false positive and false negative rates. So although your models seem to be absolutely awesome, when you go back and look at how it will perform on the actual society and on the people that it is built to help, you find that actually it doesn't help a certain subgroup. It is not helpful, and in some cases, it may be harmful. And so I just realized, as I'm looking at us, some people may not actually be familiar with what these metrics are. So just to introduce that right quick. So accuracy is the total number that you've gotten correct over your different classes over the total number that are available. So for example, out of your total of, 100 subjects, you got 96% of them correct. Sensitivity is how many times you're getting your quote unquote positive class correct. So if you're trying to predict whether someone will get COVID, then that might be the quote unquote positive class. And so it's the total number of those that you got right over the total number that are actually in the data set. The same thing is for specificity, except for your non-target class. So looking at the total number of subjects that did not have COVID that the model correctly said did not have or were not going to get COVID. False positive rates and false negative rates are related, and they kind of speak to how often you expect to see positives that are false and negatives that are false. So in that context, you can see that this is looking really good, and we would be very proud of this. Especially this differential here is quite a big problem. And so that's something that definitely would need to be addressed. So not only this, you may have found out some more information. So this is one thing that I really love about talking to the people who collect data or talking to experts in the area, because they can give you the insight on the data which you were given. So in my example, I said, the data was dropped in your lap. Sometimes it happens like that people just kind of push it on your desk and you're like, hey, find something from this, model this. And you don't really have context in which to put it in. You can only look at the data itself and maybe what you can find online. But maybe you find out some things specifically about the data. So maybe you found out that colleges and schools, so this young group, they always collect everything they can about even potential COVID cases. So they have a super robust set of information about the negative class, so people who did not get COVID or did not have COVID, and then those who do. So it's a super robust, really nice data set. On the other hand, you might find out that the hospitals that this data came from, or the nursing homes or whatever, they're just not really submitting information about their COVID patients. So maybe, there's one nurse there that, tries to always enter all the information in the form, but then everybody else kind of doesn't care or has other more pressing needs. So you find that really there is some differential way in which the information for quote unquote young people versus old people would be present in the data set itself. So in the end, even the data set that you collect is not necessarily reflecting the actual population that you'd be working on. And then the quality of the data here, for where you kind of have spurious information, is kind of suspicious. So that's also something to think about, not just the fact that your model is performing differently on a subgroup, but also that the data itself has been generated in such a way that when your model learns from it, it may be learning odd things because of the data itself. Let's talk about that just a little bit more. Oops, yeah, let's talk about that some more. So when we're talking about the things that can go interestingly with your data and the challenges that you might have in how your model performs across subpopulations, all of these things come together into a concept called fairness. And so again, they're kind of a combination of assessing how the data was produced and how it kind of is, or how it was generated, and also how we can use the model and its outputs to make sure the outcomes that we have are equitable across all of our subgroups. So there are so many types of bias that can be present in people who are collecting data, the data itself in the way that it was formulated in order to be collected, who reports the data. So for example, like on Twitter, you might find that if you did a model of the people, of tweets, you might find that the general population who may not be using Twitter would have a completely different set of behaviors than what would be predicted from the model. You might find in other data sets that have historical challenges, so that are based on, some of the things that have gone on in the United States or the history of other nations or other even organizations. The way that data is collected and the reason why those data points exist can introduce significant challenges in your data, which make the data itself quite a problem to learn from and to use. There's also information that you can look at in your data set. So for example, you can look at specific fields that seem to have high rates of omission, and that can tend to reflect whether people are actually collecting that data at all, or if it's being selectively for some reason omitted. There's also the presence of just purely omitted variables. So maybe there is really some piece of data that you really, really need that you can't get your hands on for some reason, and it affects how your model predicts. So those are some types of biases that you can think about as you're examining your data and thinking about the behavior of your data. And today we're really going to focus on addressing fairness within models. So there are many ways in which one can address fairness. There are still, this is definitely a developing area, in that there are still challenges when you combine the challenges of these biased data sets with modeling. Some things are just not resolved yet. We're looking into new ways to make sure that we can achieve fairness, even if the data itself is biased. But there are some ways that we can still work on to try to address some of the fairness that raises issues within modeling. So something that's interesting that we just talked about were sensitivity, specificity, accuracy, those types of metrics. So those are usually calculated from something called a confusion matrix. And so what a confusion matrix is it's a specific point on, let me roll back, let me try to explain that again. So when you have a model that's trying to do classification, as you know, the output of that model is not just 1, it's not just 0, it's not COVID, it's not COVID. It's actually a number that between 0 and 1 usually that reflects a score. So based on that score, you take it and you decide on a threshold at which you're going to define your output to be either COVID or non-COVID, or the positive class or the negative class. And so that's actually a value that you set. So in a lot of modeling frameworks, this is actually just a little bit hidden. People adopt the value of 0.5. So if the value is below 0.5, then that's assessed to be the negative class. So now that's non-COVID. And if the value is above 0.5, we just decided that's going to be COVID. But it doesn't have to be that way. So there are ways that you can actively change your threshold to maximize some metric. So maybe instead you care really, really, really strongly about maximizing the number of positives that you have. So you don't really care if you have a high false positive rate. You just want to make sure that you never miss any of the positives. So that might cause you to take that threshold of 0.5, slide it on down to maybe 0.3. So now the threshold of being positive is lower. So more are positive. Now that is at the expense of having more false positives, but at the same time, you've made sure not to miss any positives. So by using that strategy, you can employ lots of different thresholding techniques in order to meet some different fairness objectives. So first, let's talk about custom thresholds. So we kind of just did. So instead of using that default 0.5 that comes out of literally like most modeling frameworks, you can choose to use a different value. So the way that you would do that is you would look at first you would talk to your collaborator, whoever has input into what this model is being used for, and you would decide whether false positives or false negatives are worse or better, and how much worse or better. And by doing that, you can decide on a threshold which will maximize that metric. Now, a second way that one might go about doing that, if you're really caring a lot about the groups, so about the subgroups, is that you can use group thresholds. Okay, so before we were just talking about one single threshold. So this 0.5, this is the number. Instead, we might decide to use a group threshold. So that basically means that in thinking about our previous example, instead of just using this 0.5 across the board, maybe we stick with using that 0.5 or something slightly better for the young people. And then maybe we decide that the performance would be better on the not young people if we were to use a different threshold for them. So maybe we would increase or decrease the slider of the threshold so we can have more false positives or more false negatives, or less false positives or less false negatives. So in conclusion, if you use this group thresholding, it's just separating the threshold from this one single threshold, which is group unaware, into different thresholds per group. Now, there are also other specific metrics or specific objectives that can be met by using the thresholds. So one example is demographic parity. So demographic parity is meaning that if you have 10% of the population of your data set, which is not young, and then you have 90% that are young, then you would enforce through your threshold that 10% of the positives that result after inference should be young, and then 90% or 10% should be not young, and then 90% should be young. So essentially, the outcomes of your inference are matching the demographic distribution of your subgroups. So that could be a helpful approach in some cases. Another type is through equal opportunity. And this reflects that instead, you really want equal proportions of each group receiving the positive class. Now, in the end, that may mean that some of the smaller subgroups may just have a label randomly assigned to them so they can make up the correct amount. But equal opportunity, and that may serve some purpose for fairness in some applications. The last one is equal accuracy, and that you want, it's very similar to equal opportunity. It's just that you want the accuracy or metrics related to each of the subgroups to match. So no, not the total number of these people that is created to match, but the number or the actual accuracy or whatever metric, you want that to match. So something that's interesting about this is even in describing this, each of these approaches to fairness don't actually apply to every situation. So for example, we talked about demographic parity, meaning that if we have 10% young, 10% not young people, and 90% young people, we don't necessarily think and want to predict or enforce that 10% of the positives will be not young and 90% of the positives will be young. That may not make sense in our application. Another application where maybe that would be challenging is when you have historical data that already has a bit of bias built in. So for example, if we're talking about recidivism rates, which is whether someone will reoffend or commit another crime after previously committing a crime, demographic parity probably is not the best way to go because of over-policing in the past. So let's say that your rates of policing or rates of arrest are higher because the police have policed a certain neighborhood at higher rates and not filed arrests for other neighborhoods, then you would just actually propagate that into the future instead of working kind of to ameliorate that. So those are the kind of things that can be thought about when you're thinking about how to add fairness into your model. And it's okay if you didn't just completely get the difference between all of these. We're going to see what it looks like in practice. in just a moment. Okay. Oop, I went too far. So that might lead you to ask, why is fairness in AI important at all? So as you know, or as you may have observed, a lot of processes that we are working with in modern society, so our Amazon Echoes and our Google Homes and our auto driving cars with autopilot and all sorts of things, there is increasing automation in our society that we use. And there are ways to make that more equitable and less equitable, or just leave the status quo. And so it really is up to the person who is doing this to decide if they believe that fairness is important. But I would just say that it is important. So I don't know, it's hard to make a moral argument for this, because either you believe it or you don't. But I think that it's very important to make sure that the models that we produce and the automation that we produces equitable outcomes for all that it's applied to. So for example, that COVID model that we had before, that would be really unfair to the people that are in nursing homes, that they can't get the best behavior out of that model. Or for recidivism and policing, it's just kind of an unfair model if it unfairly targets some people other than others. It's very important because these model predictions are actually affecting the well-being in terms of health, or the future in terms of freedom, whether that they will be able to grasp those things. And with the model being unfair, it just kind of exacerbates those issues. So there are many examples of where this has introduced challenges. I keep talking about predictive policing because it is just such a fundamental one, and it just has such widespread ramifications for so many people. And that is one that has been discussed kind of at length. And even though, you know, the company at this point hasn't actually changed the way that they've looked at their models. Also, Amazon and I think other companies have tried to perform this automated hiring. So instead of, you know, this really labor-intensive effort of going and reading like every single resume and trying to figure out which are the best ones. So why not just automate that process? Have your model just read through those things and try to determine, okay, which is the best candidate, and which one should we hire specifically. And as it turns out, this approach had some challenges due to the data set itself. So the data set was composed of a lot of the people who had been hired, but there was no real assessment on whether the people who hadn't been hired would have been just as good as the ones that were hired. So it was already kind of imbalanced there. And also because of the historical imbalance of the way that Amazon had hired in the past, those actually just propagated. So in the end, they kind of just scrapped this one, and maybe they'll be trying again with maybe some enhanced approaches. Also, Twitter has recently had this issue once more. The way that it was selecting images to show, it was primarily choosing a certain demographic, and people just did not like that. And so it had some strong backlash, but you know, that's just one of the examples that, I mean, it's unfortunate, but you know, Amazon hiring and predictive policing, those have real ramifications on your actual life and well-being. So we're all at Vanderbilt in particular, I think I'm looking at this correctly. We're all at Vanderbilt. And so a lot of us are actually working on research projects that have the quality that they can affect well-being and people's futures. We study policy, we study education, we study law, we study so many things. And so we should try our best to address the problems in our data sets and in our models. And there's a really great tool that Google has for this. And I would just like to show you how to use this tool today. So let's just pop on over. Let me send you the link. I'm actually going to send you the link to the general page. And then I will send you the link to specifically what we will be looking at. Oop. So here's the link to Google's What If tool. I love the way that they talk about this What If tool, because they talk specifically about how you don't always know which metric of fairness is going to be the best one for you. So what if you tried this one? What if you tried that one? And that's what this tool is about, being able to look at your data set and really experiment around it. So let me just pull that one on up. Gotta pull that up myself. All right. Let's see. All right, let me go ahead and share my screen again. And thumbs up if you were able to make it there okay. Let us know if you need us to resend that. All right, things are looking good. So this is Google's, the page for Google's What If tool. Just to quickly take you through this, so you can get a general overview about what we're about to be looking at. It's going to look really similar to this. If you're really interested in learning about fairness or interested in learning about, kind of the state of the art in fairness, this is a great website to go to, as well as this pair code general website, which teaches a lot about fairness. So one thing to know about this is something that you can actually build into your work. So it's not just this tool that's online. It's something that you can use to interactively explore in your Jupyter notebooks, on Colab, and you can also build in cloud integrations. So what that means is if you have like models and data on the cloud, you can deploy this tool using them as well. And also there's lots of different types of data supported. So not only can you just use tabular data, which is what we'll be looking at today, but there's also image and text data able to be processed here. So if you're trying to look at different people or maybe different types of, subgroups for age to try to determine this or that from it, this What If tool would be able to help you assess that as well. So again, this is going to be a really, really great page to look at for learning more about fairness. I would especially recommend that you read over this Playing with AI Fairness article. It kind of goes over in depth what we just talked about the different ways of assessing model fairness and using thresholds to meet them. But we actually are just going to sidle right on over to the demos. And again, this website has a lot of different tutorials on understanding this What If tool.
So quick question. So the way that you would use this is you create your model, you train your model, and then you might do run your model on some set and sort of save the predictions along with all the other information, the predictors, and then upload it here to sort of explore. Is it sort of how it would work?
So this can definitely be directly in line. So this Colab notebooks, actually, I think there's a good example. No wrap on that. But I think this Colab notebooks or Cloud AI notebooks, I think both of these show really great examples of that, where the data is kind of read in line, so within the notebook, and then you either train the model right there in the notebook, or you load or establish a connection to a cloud server, and then you can plug those into the What If tool, which then displays within the notebook.
Got it. Thank you.
Yep. So let's look at an example of one of those. So what we're going to do is we're just going to sidle right on over to demos. I'm going to click here. And you should look more through these web demos. They are absolutely fantastic just to understand what's going on. But we are going to select this recidivism classification. And as we said before, there are lots of other ones to pick from. If you are dying to do one of those, the steps will essentially be the same. We're just going to focus on this one today. So let's click on that one. Let me make my screen a little bit bigger. I have to laugh at myself. I don't know why I make the screen so small, because actually I can't read it either. All right, let's see. Investigate fairness on recidivism classification. We're just going to click on the title. Fun. So if you ever run this on Colab or locally on your own Jupyter notebook, it will look a lot like this, except for it'll look like a widget that's embedded within your Jupyter notebook. So we can already see that there are some things going on here. So let's talk through a little bit of what this is and how we can use it and how we can use it to understand fairness with our data and with our models. Okay, so first of all, you can see on this page, this is called data point editor. We have this highlighted. There's something going on here with the data points, and here are some data points. Okay, that's great to know. We're actually going to skip on over to features. So click here under features, so we can just make sure we understand like what is this data set. So here we clicked on the features tab. If you have ever done EDA on a data set, this should look really, really familiar. So this is like a really, really aggregated form of a really nice EDA. About the features. I tend to call this cleaning EDA, so you understand what you're looking at, but it is really nice EDA. So what is this? So this is separated into these numeric features and into the categorical features. As we can see, we learn a lot about what is in the data, right? So we have juvenile felony count, misdemeanor count, other things, the number of priors, this determination, and this is going to be our outcome variable. So this is what we're trying to predict. We also have age, and then we have this ID, which is going to help us to do some visualization. Those are going to be our numeric predictors. So we also learned something really helpful, which is about our missingness in the data. So none of these appear to be missing, which is remarkable, but these might, for your own data sets, might have some different values there. We also learned a little bit more about the distribution, but we can also look at it here and also hover over and see some values as well. We can look at the individual bars. So that's really nice. Also, it tells you about the number of zeros. And so what's interesting is a lot of times when you have data that comes from sources where information has been manually entered, people will just kind of like put zeros where things are not supposed to be there. And so sometimes looking at those zeros can kind of help you to understand, like, maybe that's not the right value. Here for juvenile felony count, like you might think that that number of zeros is making sense. In your own data, maybe that number of zeros wouldn't make sense. So also looking at the distributions and the general counts of your data can help you to understand what you should do with it and what might be biasing it. And so EDA is actually a strong way to help you understand the bias that's in your data, like the actual numerical bias, as opposed to maybe the historical or societal bias that has gone into collecting it. So these are really nice. Let's take a look at the categorical features right quick. So we have the total number of, so this is the total number that exists. You can see it a bunch of times repeated. We have some different features for race, sex. We can see the different values here. Something that I love about this is that you can click show raw data and you get the chart version. Sometimes you just want to read the values directly. It's really nice. Otherwise, you can just hover over and see. So we can see that we have some 6 different unique values for this. Same here for sex. And then we have these 3 columns, or sorry, well, 3 columns or 3 features, which are reflecting the behavior of the inference. So inference, that refers to whenever we perform the prediction. So let's say we've already trained our model, got all that together. Now we have a model, we put in data, and we get the predictions. That process is called inference. So here we're looking at the values that resulted from inference. Essentially, there could be a 0 or a 1 because it's trying to predict the class. We also have the actual inference label. And so the inference labels are actually low risk and high risk, as you can see here, low risk, high risk. So again, and then this is the number that were totally correct. And we'll be able to visualize these as well. So this kind of gives you a nice overview of what your features are and then some EDA about those things. So even here, we can see that maybe we're about to run into some issues and maybe we should look at these to make sure that the model predicts correctly on those things. So EDA can be really helpful in providing insight on what you should look at in terms of subgroups. Okay, so now that we've kind of digested what this data set is, what we're trying to predict, let's go and start to explore it. So let's see. So now we're going to come on back to the data point editor here. So we know that this is data points. I'm actually going to make this just a little bit smaller so this legend isn't covering up some of the data. I'm essentially just rolling back my mouse, but if I didn't have a mouse, I don't know how. Well, I guess it's negative. There we go. Click this value. Okay, that's nice. That's nice. All right. So what is this? What are we looking at here? So what we're looking at here is the scatter plot of some default value on the x-axis. That's just something that is made up to help, jitter the position so that we can see it. And then we're plotting that against the inference score. So we talked about this a moment ago, in that when you're trying to do classification, you don't get the label out, you get a score out. And so this is all the scores across all of the participants or all of the subjects. So that's what's going on here. So let's see, we can see that the colors here are reflecting the actual label or the inference label. So what was predicted. So whether these people were predicted to be high risk, which is here, and low risk, which was here. And we can see that these colors are reflected by this selection, which is called inference labels. So we could also change a different value here. Maybe we wanted to look at something different. So let's see, maybe we want to look at, I don't know, race, sure. So here we can see that our legend changes. Now we're looking at these by race and inference scores. So what's interesting about this coloring is that it can start to help you visually see how your model is predicting. So something that I would suggest is to go and change this x-axis to the data point ID. And this helps it to kind of have this standardized x-axis, because otherwise it seems to just switch around a little bit. So we switch this on to data point ID, and let's switch this back from label by to inference. What do we have before? Inference label. Oh, wrong thing. Well, it is a teachable moment. So you can see what the behavior of that was. If we add an inference label, it only labels the data point. Well, not only, but it labels the data points. And so you're able to see another dimension of what these things are based on that setting. So it just adds another dimension if that's something that you're able to kind of digest, which may perhaps work for smaller data sets. Oops. Okay. We're making it. All right, so I'm going to switch that right on back over. Let's color by, go back to inference score now that we have data point ID. Sorry, I'm just not doing well. Let's see. Inference label. That's what okay. So now we have the data point ID along this axis. And we have the inference score along this axis. And we can see the coloring by the inference label. Can anyone guess what they think the threshold here is that's being applied to determine the high risk from the low risk? So what threshold do you think is being, ooh, wow, quick today, yes. So this, when this starts, it starts with a default threshold of 0.5. And so the classification here is done on the scores on 0.5, where everything below it's going to be low risk and everything above is going to be high risk. So now that we've looked at these inference labels, maybe we want to, now that we have data point ID and inference score, maybe we want to see the ones that are correct. So let's look at that. Inference, we're just going to change the coloring on this so we can see which ones are correct. So inference correct on that one. Interesting. That's interesting. So first of all, if we kind of go back a little bit, we can see that there are kind of some challenges here in terms of the classification. So we can see that, I don't know, I know that it's just kind of scattered regardless of score, even though we do kind of see that there are a lot of incorrect, particularly gathered around the 0.5 section, because that is kind of a hard area to kind of understand. So now we might think to ourselves, I wonder about these ones that had like a really high score that were incorrect. Like, how can the model be so confident? And what is making the model so confident about these ones that are just tremendously incorrect? Like this one right here is literally almost on the one, and it is incorrect, as we can see in red. Well, what happens if I just click it? Oh my goodness. So what happens here is that I can learn a little bit more about this point. So let's see, what is this point? What is this scenario? Well, this subject, again, they should have been classified as no risk. Instead, they were classified as high risk. So why, what is making them do that? So let's see, we have that they were 59. They don't have any of these things, but they do have a bunch of priors. African-American male, interesting. Maybe I wonder to myself, you know, like how different are they from a person who would have had a positive score here, or who would have actually been classified as low risk. So this person here was classified as high risk. What is the person that looks like this set of features but was classified as low risk? What is the person who looks most like them? Where is that dividing line? Well, we can pick that out. And the way that we can do that is by turning on this nearest counterfactual. What does counterfactual mean again? Wonder what this I does. Oh my goodness, it's going to tell me. Nearest counterfactual. It's going to compare the selected data point with its nearest neighbor from a different classification using either of these two types of distances. Yes, you can also use a custom distance function. So let's see, let's just look at this. Nearest, we're going to turn that one on. I guess we'll use the L1. Maybe L2, because there's a lot of numerical variables in there. All right, let's see. Really wasn't all that helpful. So this person was classified as low risk. And again, if you look here, it's at the bottom of my screen, unfortunately, but you can see here how the predictions are. So this person was predicted to be high risk, this person over here, and that was the score that was awfully high. This person was predicted to be low risk. Scores awfully median. They were on the cusp there. So what is really different? What is different about them? Well, one, this is different. And we can see that this is highlighted in green. This one is different, little fewer priors, different this, and then the actual class is different. Well, that didn't, I don't know if that was like overly helpful. Maybe my curiosity is what would I need to change in this to change this person from high risk back to low risk? And if you're having trouble turning on nearest counterfactual, make sure that you have selected the data point. So here, if I click on nothing, this is kind of now I can't make a selection. But make sure you click on a data point. So actually to that point, let's click on a different data point. Let's choose an incorrect down here at the bottom. It's false negative. Click on this one. Let's just, oh, nope, didn't get close enough. All right, there we go. So we click on that false negative. This is activated again. Here, there we go. Let's turn that one back on. Here we see that this one was super predicted to be low risk, but they actually had this recidivism. And let's see, so the nearest person to them, most similar by the L2 score, is going to be this 49-year-old person who was this 10 priors, this one. Interesting. So again, like I was saying, like I may wonder, like what can I do to make this specific person go back down, like become high risk instead? So what would need to change in their feature set to instead be higher risk? Well, maybe since this was the difference here, maybe if I change this to 10, that would make them go into the high risk category. Because again, they were predicted, like super predicted, as being low risk. So let's see, how can I change this to 10? As it were, I could just click on it, change it to 10. Sorry, that is not how that works. 10. All right, let's see. So don't press enter, that's not how that worked for me. And then now that we've changed that to 10, maybe what we want to do is create a new prediction on this new person with their new values. So let's see how that impacts our risk. So let's predict. As you can see here, now that we've turned this, into a 10, we can see the difference. So we can see here, this was our first run. This was the initial prediction that we were looking at the beginning. This is the one that we just did with priors count equal to 10 instead of its original value of 0. So now this actually made them a little bit more high risk, right? So increasing the priors has made them more likely to be a high risk person. So that is something that factored into this person being classified as low risk because they had a low prior count. Let's see, what else? We may also think to ourselves and looking at the nearest counterfactual. So this is a new one. We may also think to ourselves, what would I need to do with any of these other factors which would influence whether this person is classified as being high risk or low risk? Like if I were to just look at one of these individually and go through the full range of values, I want to see the likelihood, or not the likelihood, but what causes a change between them being low risk versus high risk. Luckily, there's a whole function for that. So that's actually called a partial dependence plot, that functionality that we described. And so if we select a specific individual or a specific subject, we can use partial dependence plots to look at the changes to the classification based on sweeping through those values for that particular person. So let's look at this. So this is going to be the partial dependence plot for age. And we can see here that what we've done is we've taken the model and we've taken the subject. So the subject has all these different values. We've held them constant. Just fix those. And now we're taking age and we're evaluating the model at all of these different values, every single one of them. And we're seeing at each of these different points, what is the resultant inference score? So something that's nice here is that this plots the threshold for us, right? So this is the threshold at which we would know that something is positive or negative. And so we can see here that the younger we are, or the older we get, the more it tends to lower the inference score. So we go from potentially being high risk up here to being low risk down here. And then kind of the inflection point is going to be around 50. So once you cross over 50 for this particular person, then they would start to be classified as low risk if everything else is held constant. We can look at the other fields as well. Maybe we're interested in priors count. So now we're looking to see how many priors could this person potentially get before they are classified as high risk. And it looks like currently, as you increase the priors, you also increase your risk score. And so that's meaning after even 12 priors for everything else held constant here, this person would still not get the high risk. They would need to up those priors. Well, that's interesting. So we saw that for this specific model, or for this specific subject, when we swung age up, it kind of decreased this value. And then when we increase the priors, it also increased the inference score. But maybe we want to look at that in mass. Maybe we want to look at the scatter plot of the relationship between priors and the inference score, or maybe age, the inference score? Well, we can certainly do that. So here we're going to go to the data points pane again. And what we're going to do is we're just going to change the x-axis. So whatever we're plotting, we're going to plot it against the inference score. And we'll just keep this inference correct. So let's see, let's look at, what did we say? Age. Let's look at age versus inference. And actually, it may be helpful to look at the actual inference label. So basically what this is trying to tell us, it looks like, is sort of, in general, the older you get here along this axis, it tends to be that your inference score is going to be going down. Now there are like some special cases kind of up here, but it tends to be, in general, this tends to be the sweet. And it also seems like after a certain age here, oops, after a certain age, it's not really wanting to classify you as high risk at all. So maybe this is how this person kind of escaped that classification. Maybe let's look at something else. What did we say before? Priors count. That could be interesting. Ooh, well, that's interesting. Well, we see here again that on the x-axis, we have the priors count. And we can see that as the priors increase, we can also see that in general, the inference score also increases. So essentially, after a certain number of priors, especially at this threshold, after a certain number of priors, except for this special guy over here, it's always going to try to label you high risk. So once you get over this point over here, you're going to be high risk unless the threshold ends up being very, very large. So these types of analyses can really help to just give you insight into some things that are going on with your model. Something else that comes to mind about this is that this workshop really is about fairness. However, I can definitely see where these would also be helpful in just analyzing the performance of your model to understand what's going on. So I'm thinking about a project that is going on that works on images, and the desire is to understand how the relationship between the image and the classification, and having these sorts of abilities to do experience, especially this nearest counterfactual, would really help in understanding why one was classified as one way versus another way. So I think that this could be just general purpose use. And if it does become general purpose use, you'll know just how to transition over to making it into a fairness model as well. So now let's actually get to the fairness parts. Okay, let's look at this. Really pumped. So that's this middle bar. So let's click that one. Okay. And first of all, we can see something interesting. So let's just start by looking over here. This is looking very familiar in the numbers, confusion matrix, curves, performance curves. And do keep in mind that the ground truth that we're using here, the thing that we're trying to predict is this recidivism within 2 years. So here we can again see that where we are is we're using this threshold of 0.5 on all the data points. And we can see that the number of false positives, the false negatives, and the accuracy overall. Here goes the F1 score as well. So if we're interested in kind of understanding how that's going to influence the performance of our model, what we can do is either drag this. Oh, we can drag it, and we can see the performance changes here or through here of our model. So like we said before, if we're really, really, really not wanting any false negatives, we could just lower this down. Let's get there. And we can see the more that we lower this, we can really drive those false negatives down. But the question is, now we've really, really, really increased our false positives. So now everyone has recidivism. In this particular case, we might, there's probably a trade-off here. But maybe we want to increase this a little bit more so that there are no false positives. And we can do that by dragging up this threshold. And right now, I'm just pretty much looking at these two. It's a lot to look at, but is very helpful as well. But here in dragging up this threshold, we can see that this does minimize the number of false positives, as expected, at the expense of the false negatives, as expected. So, rolling back to our previous conversation. Hold on, let's look at single threshold. So this is the same, right? So rolling back to our previous threshold, or previous conversation, we said that maybe it would be helpful to look at subgroups, and not even maybe that it would be helpful, you should look at the subgroups, period. So now we're going to slice by those subgroups that we might be interested in. So one that we might be interested in is the age. And because this is a numeric variable, we want to bin this into buckets like these. So maybe we just want to increase those buckets, maybe to, no, 5. Now we're at 6. It's okay, bring it back down. So now we have our new buckets, right? And we said that we're at custom threshold, right? So this is custom thresholds for everybody. Let's look at single threshold. So here you can see the effect of what the single threshold is, right? It wants to set the same exact threshold for everybody. And now you can look at the performance for everybody across all of the different subgroups. So again, these binned ages are listed here. So these are now our different subpopulations based on age. And we can see here that the model is doing on these lower ages or these younger ages, but here it's doing something that's nice also is that it gives you the counts of each of these subgroups. Sometimes when you look at these, like it's hard to think about like this 88%. Like that sounds really nice in context, but it's hard to really appreciate that there are only 34 here. Whereas here, this is 130, almost 2,000, and then the accuracy is this. So now let's look at the different thresholds as well. So we talked about that demographic parity. We're trying to get the same ratio of the demographics to the number of outcomes. So let's see, let's click on that one. So now we can see the effect of forcing that particular metric of fairness on the thresholds. So you see different thresholds set in order to achieve the correct ratio of the outcomes in the data. So that is what demographic parity is. Yep, I agree with you. There's a lot more data on that younger age. Yes. Then let's look at these other different metrics here. Here we go. Let's look at equal opportunity. Wait, what was equal opportunity again? Can someone remind me, like, what can I click on to remind myself about what equal opportunity is? Do you think there's anything here that I can click on that would help maybe explain what that is if I don't remember? Oh, I love that. Oh, I just clicked the wrong thing. Whoops. All right, here we're back. All right, this eye icon. That's exactly right. I love these help menus. So this one is saying that equal opportunity is meaning that among those data points with positive ground truth, there's a similar percentage of positive predictions in each slice. So we want to make sure that there's a similar number of positive predictions in each slice, even if that means that we need to assign some people to that slice who would otherwise be not in it. So let's see. We can see the effect of that labeling here. And so here we can see that our thresholds are kind of changing. We can look at equal accuracy and see something similar. Gotta get there. Equal accuracy, you can see that it's getting there. It's getting there. This might be the best that the model can do to try to reach this. This is kind of interesting here. It's very interesting. So this accuracy being what it is, similar across things. This seems like it's a really good result. But when you look at it next to the F1 score, like you would think all of these values should be about the same. The fact that they're not and the accuracy is the same is telling you something about the composition of the subgroups data sets. So this is reflecting that there's a high likelihood that there's imbalance in the subgroups. Okay, let's see. And then group thresholds. All right. Let's click on this one. Optimize a separate threshold for each slice based on the specified cost ratio. So I love this point that they bring up the specific cost ratio. So thus far, we've used a cost ratio of 1, meaning that the false positive and the false negative, those are equal in our eyes. Like if we accidentally, say that someone is gonna, commit another crime and they don't, that's as fine as if someone does commit a crime and we said that they did. Like those two things are fine. So that's a decision that has to kind of be made. But we can integrate that into our analysis of the thresholds. So what we can do is we can go ahead and just change this cost ratio. And now we see that we start seeing some different values. Oh, no, didn't mean to put that up. So setting this to 4 is just basically meaning, hey, the false positive is 4 times as bad as that false negative. I really don't want any false positives. So we can see that the thresholds are changing there. You can see that they're much, much higher. Interesting.
One thing that strikes me about this is we're talking about really, in some case, life or death decisions. And it kind of, on one level, it kind of looks like all we're doing is we're changing thresholds, and all we're doing is sort of making some data science solutions, data science decisions about the models. But these are policy decisions, and these are decisions that are affecting people's lives. And it's stunning to me to sort of see it play out like this. We can easily just change the numbers, and it makes me wonder about what Compass did when they were first creating this model, because they used 0.5, for everything. They didn't account for any of this. They didn't care.
Yeah, it is really interesting to see how that is affecting like these outcomes, and it's just really interesting to just, I don't know, just consider the situation. But what's nice is that we all are continually learning, and I think a lot of us currently are in school, and so these are things that we can learn to think about within the work that we're doing today and tomorrow, and we can carry this forward with us into our careers so that we'll be able to deliver these models that are so much more, they're so much more fair and better for everyone in general. So giving y'all, passing the torch to y'all. All right, so something that's also cool about this is once you set these thresholds, okay, you can see the impact of those thresholds back on your data point editor. So here, voice cracked. So again, we said here that false positives are super, super bad as opposed to false negatives. And so now we have everything pretty much classified as low risk because we didn't want any false positives, none. So now let's go back and make this maybe more reasonable. Maybe it's 2. And then maybe let's grab one of these different metrics for fairness. Let's do maybe equal accuracy. And so now what this is going to do is it's going to set these thresholds, and then it's going to come back and apply them as we look at them in our data points. So let's take a look there. Interesting. So you can see kind of a different result here. I believe the trend that we had from before is a little bit different. Let's just roll back to the original data point. Yeah, inference score, inference label. Kind of see here. This is maybe less here. Let's look at the ones that are misclassified. Actually, that are classified correctly. Maybe we did better, maybe we did worse. But for the subgroups, we look at them, we may have done much better. Now we can look at these a little bit more. So again, let's take out one of these incorrect ones. Here at the top, this is somewhat different. So here again, we might look at this and say, okay, wow, 39, wow, 27. These are pretty close. And yet this person, oh no, these are both classified as high risk. Let's see. Partial dependence response. Oh, I might have just that again. So let's see. Oh, this is going. It seems like we might have run into an error, perhaps. It might be because of the threshold that I've set. Yeah, I think I might be running into a little bit of error. Might need to refresh. I need to refresh. It's okay. So I'm just going to lose everything we just done, I think. That's okay, because I think that you all have grasped what the basic point of and how to use this tool that will be able to assist you in your work. So now, so what questions do you have about this? Elijah?
Yeah, I was just curious. I think I noticed that the data set that we were looking at there was something on the order of thousands of data points. And like for stuff that I'm doing, I'm working with data sets on the order of like millions and tens of millions. And I'm curious if you like, I haven't looked at any of the other demos. Maybe I could just find that there. But do you know how this like system scales up? Like, does it get really slow once you start putting that many points into it? Or like, do you have any experience with that?
So I am not sure about how it scales up, but I am sure, or maybe I'm pretty sure that you can select, like you could subsample what you would put into this data set to look at. So you might not choose the full like thousands or millions to put in the data set. You might just choose a representative sample to look at.
Ah, okay, that makes sense. Okay.
Other questions? Yeah.
Yeah, I was just curious because my work is pretty genetic in nature, and so it's very hard for me to like go into individuals' data and like essentially like track their backgrounds and stuff. So I was just wondering if you had any insight into how you could work with like protected health information or instances where you really don't have the full picture of the people you're sampling from.
That's a really good question. I mean, my general thought is that as much as possible, you should try your best to make sure that your model is fair. But if you've really exhausted all your avenues, then you really just kind of try to do your best. Also, there is the question of, kind of elevating your, access. And so requesting access to that kind of data, maybe it's like de-identified to some extent. but just having enough credentials to be able to get to that, or taking whatever training that you need, or requesting for whatever collaborator that you need. Jesse, what are your thoughts on that?
Sometimes sometimes you sort of need to take a step up too from where you are. So maybe you're not, because really what you're looking for is the downstream effects of the decisions that you make about your model. So that's one thing. It may not be, you may not be able to do this full counterfactual, but you might be able to say, to do a post hoc analysis that's maybe not quite so interactive. De-identified data is a great way to go. Anonymized data is another way to go. But in my opinion, the most important thing is to at least ask these and raise these questions of what are the differential impacts of your models, because sometimes it sneaks in. So, for example, with research around genetics, for example, having to do with tests, or with again, looking for even just answering the very specific, simple question is, how well does the model perform in different subgroups? Even if that's the only thing that you can get to because you don't have access to any of the other information, that still is valuable. So something is better than nothing.
Any other questions? All right, so I would love for you all to go into breakout rooms for about the next 10 minutes. It sounds like you all have some really great projects that you're working on. And I think it would be a great opportunity to bounce your thoughts off of other people and discuss with others what some great approaches for implementing or assessing or using fairness ideas in your work may be. I also think it would be really great to also discuss your actual data and try to assess whether or where types of bias may have sneaked in, and how you might be able to address those also within your model. So we have a breakout room document. Thank you, Preston. Let's see. And would you mind sending that out? And that should contain the question and also some of the links that we went to today. We'll do about 10 minutes, then we'll come back and close up.
I have a quick question for the TAs. For first, would you like to be in separate rooms, or to have people sort of spread out? Research or the people currently working on projects may be sort of distributed. And first folks, you may not have a particular model that you're working on right now. So TAs, what are your thoughts? Distribute around or special rooms?
I think it could be nice to distribute so that we could hear some ideas.
Okay, great.
Yeah, and there appear to be more First Center folks here than any other group, so maybe it would be better to just split them so that each group has a relatively equal amount of people in it.
Okay, great. So let me go ahead and just take a quick moment, and I'm going to distribute folks around. Let's see here. It will take me just one quick moment, just so I'm going to choose some folks that don't have research and folks that we definitely know have research going. Great. All right, I'm going to go and open up the rooms, and you said 10 minutes. All right, I'm going to automatically move people into the rooms, get a 30-second warning, and 10 minutes. See you all in just a moment, or 10 minutes.
Hey, I think I was placed in an FC room. Is that
Oh yeah, it's
we're all
mixed.
mixed?
Yeah,
Okay, cool.
and if you could share, yeah, if you could share your research with them and sort of discuss it. Yeah, do you need me to come in there? Do you see?
No, it's all good. I was just kind of curious about.
Yep, you're good.
Okay, cool. Could you put me back in?
Let's see.
Sorry, I was in room
No,
4.
that's quite all right. You were in 4, and I might have to move you around just a. Actually, are you up here? No, I'm gonna have to move you around just a little bit. So I'm gonna pop you someplace and then pop you back.
All right, I think we have just a little, we have a few more seconds of breakout rooms. Yep, about 8-7 seconds. All right, so I think we're right here at the end of our time. Otherwise, I'd really love to hear more about the things that you discussed. Actually, I still yet would love to hear more. So if you're on Slack on Data Science Institute's organization or on our organization, please send me a message because I want to learn more about what you're doing. Otherwise, please feel free to reach out to us about any questions that you have. I think our next workshop will be next Wednesday on modeling NH2O. All right. Well, thanks again for coming, and I hope to see you guys next week.
See you guys.
Bye.
Thank you, everyone.